In this video, we are going to be talking about Laplace transforms, which I believe was covered in your differential equations class, if you took one, and a particular application or use that we get out of Laplace transforms when we're studying system dynamics and vibrations. Um, so just by way of brief review, so Laplace transforms allow us to change from a time variable to it's a change of variables that allows us to more easily analyze and solve differential equations. So you may or may not remember that um, if you have some or some equation f, right? Um, some equation f of t, then the Laplace of that equation f of s is given by some fancy L uh, of f of t. So the Laplace of f of t is equal to the derivative from t equals 0, or sorry, not the derivative, the integral of t equals 0 to infinity of f of t times e to the minus s of t, s times t dt. And you probably looked up the Laplace of some common functions in a table. What we mostly care about, what we're mostly going to be looking at is the Laplace of some function f and f of t and maybe a derivative f prime of t and f double prime of t. And that Laplace is, so f of t just goes straight to capital F of s. If you have f prime of t, that's f, or s times f of s minus your initial condition, um, f of 0. Oops, it's not supposed to be a theta. F of 0. Um, and f double prime of t goes to s squared f of s minus f of 0 minus f um, minus s times f of 0 minus f prime of 0. And then if you have if you have an input or a unit step, f u of t, the Laplace of u of t is 1 over s. So when we're looking at, for example, some sort of second order differential equation, maybe it looks like y double dot of t, or y double dot plus 7y dot plus 12y equals some inhomogeneous input. If we use initial conditions equals 0 and we take the Laplace, what we're left with is s squared y of s plus 7s y of s plus 12 y of s equals f of s. And what we're going to define is what's called a transfer function. Um, a transfer function, we'll call it g of s, is by definition equal to some y of s, so it's the Laplace of your dependent variable, divided by f of s, which is the Laplace of your input. And so in this case, if we factor out y of s, we're left with s squared plus 7s plus 12 equals f of s. And if we're looking for the fraction y of s over f of s equals g of s, That's going to equal 1 over s squared plus 7s plus 12. And so this transfer function, so for one, the poles of the system are also the same as the poles of the transfer function, which is when the denominator equals 0. So the values of s to make denominator 0. So that s squared plus 7s plus 12, that's the characteristic equation for this particular system. Um, we're also going to introduce a term called the zeros of the function, which is the values of s to make the numerator 0. This one doesn't have any zeros, but if you had a polynomial in that numerator, it would have zeros. And these transfer functions allow us to start to think the um, about the frequency response of a system, about the response of a system if that f of t is a sinusoidal input. And we do that by talking about what's called the sinusoidal transfer function. And the sinusoidal transfer function is just if you take the transfer function g and you plug in j omega wherever you see an s. And remember, j is, we're talking about the imaginary number. In the past, we've called it I, but now since we've started introducing current, we use the letter j. Um, the sinusoidal transfer function, g of j omega, for this example that we're using, is just 1 over j omega squared plus 7 times j omega plus 12. And that is 1 over, so omega squared is omega squared, j squared is minus 1, so minus omega squared plus 7 omega j plus 12. Um, and this is now in the numerator. In the denominator, we have a complex number. It's a vector. We have, I'll write it again here, we have 1 or 12 minus omega squared is a real value plus 7 omega j is a imaginary value, and that's just a complex number. And we can get the magnitudes and the phases of g of j omega of the sinusoidal transfer function, and that's going to tell us the magnitude, ratio, and the phase offset of the steady state solution to a harmonically forced system. So if we'll recall y of t, y steady state of t is going to be equal to b times sine of omega t plus theta plus phi. And in this case, so b is the magnitude of the response, amplitude of the response. Theta is the offset that was already there, and phi is a phase offset that exists in between an input and an output of a harmonically forced system. And b is equal to a bar, which is the original input to the system, times the magnitude of g of j omega. Um, and phi is equal to the phase of g of j omega. When we're talking about the fraction, when g of j omega is a fraction, if we go back to how we talk about complex numbers, the magnitude is the magnitude of the numerator divided by the magnitude of the denominator, and the phase is the phase of the numerator minus the phase of the denominator. So let's do a quick example. If we have y double dot plus 2 zeta omega n y dot, plus omega n squared y equals f of t. Then if we were to take the Laplace with initial conditions 0, you always say the initial conditions are 0 with a transfer function. We're left with y of s times s squared plus 2 zeta omega n s plus omega n squared equals f of s. And so g of s equals y of s over f of s equals 1 over s squared plus 2 zeta omega n s plus omega n squared. Well, then let's go ahead and plug in g of j omega, and I'll use capital Omega because this is the driving frequency of the system, equals 1 over j omega squared plus 2 zeta omega n times j omega plus omega n squared. And so let's rewrite this. We have 1 over, so j omega squared is just minus omega squared. I'll take this omega n squared right there and add it right there, plus 2 zeta omega n omega j. And so the magnitude of the numerator, I'll just go ahead and say the numerator equals 1. The magnitude of the denominator is going to be the square root of the real part squared, omega n minus omega squared, plus the imaginary part squared, which is 2 zeta omega n omega squared. Take the square root over all of that. And this might start to look familiar based on that equation that I told you we would derive for the magnitude of response. And so the magnitude of g of j omega is equal to magnitude of the numerator, which is 1, divided by that whole square root. So omega n minus omega squared plus 2 zeta omega n omega squared. Take that whole square root. And I'll rewrite this in terms of a ratio. So it's 1 over omega squared times the square root of omega n over omega squared minus 1 squared plus 2 zeta omega n over omega squared. We'll take this whole square root. Same thing, the phase of g of j omega equals the phase of the numerator minus the phase of the denominator. And what that comes out to be is a tan 2 of minus 2 zeta omega n omega n squared minus omega squared, which is also equal to a tan 2 of minus 2 zeta omega over omega n 1 minus omega over omega n, and square that whole thing. And so the sinusoidal transfer function has allowed us to rederive those equations that allow us to get the magnitude and phase of the steady state solution. And we can now do this more generally. We'll go ahead and stop that video there.